All right, so for this one, it says you're lying on the beach and your eyes are 20 centimeters above the sand. Just as the sun sets, fully disappearing over the horizon, you jump up immediately. So I'm going to pause right there. Let's kind of draw a picture of this. So I am I'm on the earth like this. We'll make it a little bigger because there's a point to this. And here I am. I'm laying on some sand. So this is where I am, somewhere over here. Okay. And then I'm laying down. So this is my head, 20 centimeters. Right? And I'm laying down, and my line of sight is like this. Okay? And just pretend that's a straight line. And I'm looking at the sun, and the sun sets. Okay? So that's where we're at right now. So then it says, immediately I jump up. And I jump up to 150 meters above the sand. And you again see the top of the sun, and you count a certain number of seconds until the sun fully disappears. So now you got to keep in mind that the Earth, this Earth rotates like this, right? So in a fraction of a second, the Earth rotates, and now I'm over here, sort of, right? So as the Earth rotates and I stand up, I'm probably like around here somewhere. Whoops. So now I'm standing up, and I'm looking again, but now the sun appears to be at a different angle, right? So now because I'm standing up, when I see the sun has moved a little bit. Like down here, sort of. But because I stood up, I could still see it, okay? So, and I'm exaggerating my location. If I just stood up, I'd technically be standing here, but I'm exaggerating it on purpose. So then this thing becomes, oops, my line of sight looks like this. And relative to the Earth, we can almost pretend that I'm almost in the same exact location. When you compare, when it's relative to the Earth and relative to the sun, I do move for just a second or two. Okay? And if I extend those lines in the other direction, this line goes like this. Okay? My second sunset goes like this. There's going to be an angle here, and we call that angle theta. And if I want to, I could think of it in terms of, I'm going to erase this other one because the second one is the one that matters. So let's label some things here. So this is the first sunset, and this is the line of sight for the second sunset. And this is my angle theta. So whenever we see this is the Greek letter theta. And that is just usually used for angles, but you guys should know that from your geometry classes, right? If you don't, now you do. And if I think about the center of the Earth, and I draw a line from the center of the Earth, I can think of this as kind of like a right triangle. And this would be a right triangle. Coincidentally, this right here would also be theta. This angle right here. Now the distance from here to here is a radius. The distance from here to here is a radius. Yes?
Why are they both theta?
They're the same. They're congruent. They're the same measurement. Okay. And then the distance from here to here, we're going to say the height. Okay. Now the height is how much I stood up. Right? So my height then, we'll talk about the height in a second. But then there's also this measurement here that we'll call the distance. Now the distance I really don't have any information on. If my eyes are 20 centimeters above the sand and the sun sets, my line of sight to the top of the sun has got to pretty much be tangent to the Earth's surface. So when I'm lying down at point A, I see the sunset. And then when I stand up, elevating my eyes by the height of 150 centimeters, right? And there's two ways to look at that. You could think of it as 150 centimeters, or you could think of it as 150 minus 20. But you'll see here in a second that's not the most important. I'm going to do it this way. 30, because you're at 20, and then you're going to jump up at 30. And relative to the Earth's size and the distance to the sun, we could think of that as being tangent. Now, if it's tangent, then whatever this has got to be 90 degrees because it goes towards the center of the Earth. And then distance is what we don't know. That's kind of the thing that's going to be helpful to us to answer this question, but we haven't even got to the question yet. So then I stand up, and then it says, if you count the number of seconds, t, until the sun fully disappears again, you can estimate the Earth's radius. Then it says, but for this problem, use the known radius of Earth to calculate the time. Okay? So if we knew the time, we could figure out what the radius of the Earth is. But now they're saying just use the Earth's radius. So before I plug this in, if I rotate this and think about this, I have, well, let me draw this a little better. What I really have is I have a right triangle that kind of looks like this. A perfectly drawn right triangle. Where this is 90 degrees, I have this measurement for theta. The distance from here to here is d. This is r. And then I have r here. And then I have h here. And then the length from here to here is the arc length from A to capital B. Okay? We'll work with that later. So using this is a right triangle, so the Pythagorean identity, if I think about this, this is like, if this is A and this is B, then the sum of these two would equal to C, right? In other words, if I say A squared plus B squared equals C squared, I would end up with D squared plus r, capital R squared, is equal to r plus h squared. Does that make sense so far? Okay. So then what I need to do is I need to expand this. So if I multiply this out, r plus h times r plus h is going to be r squared plus 2hr plus h squared. And then that's also equal to d squared plus r squared. Now if I subtract r squared from both sides, I get that d squared is equal to 2hr plus h squared. And then here's the interesting thing. When you think of the radius of the Earth, right? And if you're just curious about what the radius of the Earth is, the radius of the Earth is 6.38 times 10 to the 6 meters. Whether this is 130 centimeters or 150 centimeters, it's really small. Several orders of magnitude. So when I'm calculating the distance, I can basically just toss this out. I can think of this as being almost negligible, not significant, compared to the actual radius of the Earth. Why would I do that? Because it'll help me get some stuff done, right? So if I do that, I can think of it in terms of this is almost 2hr. Notice I use the squiggly lines, that means approximate. But if I look at D, D is actually also the opposite on my right triangle. And R would then be the adjacent, right? I'll let that soak in for a second. Does that make sense? And remember that tangent of theta is equal to the opposite over the adjacent, or tangent of theta in this particular case, what's the opposite? Well, the opposite is D over the adjacent, which is capital R. And so if I solve for D, I get R times tangent of theta is equal to D. Well, if I square that, I get r squared times tangent of theta squared, and I can substitute that in for D. In other words, if I take this and I square it, I could just plug this in and substitute it in for D. Now I'm going to stop. Do you guys see that? Does that make sense what I'm doing? Now you might ask yourself, how in the world would I know to do that? You wouldn't. That's why I'm teaching it to you. It's why I assigned it. But eventually what happens, the more you do these types of problems, your brain just starts thinking, how can I do that? I'm going to use some sort of trig function. I'm going to do this. I'm going to do that. And it does click eventually. So now this is equal to 2hr. Right? Well, now if I solve for r, because r is a known thing, right? I can first I divide both sides by r, and so I get r tangent squared of theta is equal to 2h. And then I divide by r, or no, I divide by tangent here. Why is Mr. Adams solving for r? Well, I want to solve for r because I know what it is. Okay. And I kind of know what h is. And I can figure out tangent of theta at some point in time. So I'm going to have to go to another page on this problem. This is kind of a difficult problem. So with that being said, on the next page, this is problem 35 continued. I end up with r is equal to 2h over tangent squared. Now, I know what r is, I know what h is. What is it that I don't know?
Theta.
I don't know theta, so I got to solve for theta. So now, what I'm going to do is I'm going to multiply both sides by theta and then divide by r. In other words, essentially, I'm going to swap these two. That's a thing you can do. So then I end up with tangent of theta squared is equal to 2h over r. Now, I wanted to do this in the beginning. I don't know why the textbook made us go the other route. But that's what the textbook did, so I stayed with whatever the textbook said. So now what I need to do is I just want tangent, because if I use the inverse of tangent, I can find out what theta is. But I need to take the square root of both sides. So I'm going to take the square root of this and the square root of this. And I get that tangent of theta is equal to the square root of 2 times h all over capital R. Or tangent, oops. Now to get theta, I just take the arctan, the inverse of tangent, right? So down here I would say that theta is equal to tangent inverse of 2h over r, right? Is that right? You guys with me so far? Does that make sense? Have you guys all had trig? You haven't had trig? Who has had trig? You've had trig? Yeah. Okay, maybe we'll go over this a little bit more. But this is what you do. So when you take the inverse of tangent, this is something you can plug in the calculator. But basically, well, I'll just go over it now. If I have tangent of theta equals the square root, this is kind of a side note to show how this works. Actually, yeah, we'll just finish it this way. What I really end up doing, remember how like if you want to solve an equation, you do the opposite? Well, technically you do the inverse operation. So in order to solve this, I need to do the inverse operation of tangent. And so I take the tan inverse of both sides. And so the tan inverse of tangent of theta on one side, and then the tan inverse of 2h. And so these two undo each other, right? This undoes the tangent of theta, and so you're just left with theta. and this is what you're left with. Tangent inverse of the square root of 2 over h, or 2 times h over r. Okay, so this is where we're at now. Except I know these numbers, so I could say that theta is equal to arctan of 2 times, now we said that we were 130 centimeters. What is that in meters? 1.3 meters. So we have to make sure that we're always using SI units. So I'm going to plug in here 1.3 meters all over 6.8 or 6.38 times 10 to the 6 meters. Okay. So then when you do the math on that, theta, this is a very small theta, it is 3.66 times 10 to the negative 2 degrees. So it's very small. Well, what is that? How does that help us with regards to seconds? Well, we got to go to a third page. We're almost done with this problem.
Does that say to the power of 0?
Huh?
Does that say to the power of 0 at the bottom?
No, that's degree, like the degree symbol. I'll write it out though. So theta then is, I'll do it without the scientific notation, is actually 3 point, oops. So this is actually 0.0366 degrees. Okay? Because we're solving for an angle. And that angle is measured in degrees. Are you guys with me so far? Okay. All right, we're going to do one more page and then we're almost done. So what does that mean? Well, for problem number 35, if I have a measure of theta, and that is equal to 3.66 times 10 to the negative 2 degrees, how do I figure out the time? Well, I know that theta is equal to or proportional to 360 degrees. And proportionally, if I think of t seconds, okay, I've got to convert that. Well, how many hours are in a day? 24 hours, right? Times 3,600 seconds over 1 hour. Okay? So there's 60 seconds in a minute, 60 seconds in an hour. Basically, it's one full revolution, right? So 360 degrees, if we measure that, one revolution of the Earth is going to be 24 hours. But how does that translate to seconds? Let me write it another way. I think it will make more sense. So we all agree that one full revolution of the Earth is 24 hours, right? Okay, so what I'm doing is I'm comparing an increment of the whole. This is the part. This is the whole, right? This is a little bit of the rotation of the Earth. This is a whole revolution of the Earth. This is a little bit of time, and 24 hours is how much it would take for the Earth to rotate the whole time. But I need the answer in seconds. So we'll do it like this. 24 hours times the conversion ratio. 1 hour is how many minutes? 60 minutes. And then 1 minute is equal to how many seconds? 60. What's 60 times 60? At 3,600 times 24. So if I multiply this all the way across, right? What's 3,600 times 24? I think it's 86,200. I mean, I could be wrong. So we'll say 24 times 60 times 60, 86,400. So this is equal to t seconds, 86,400 seconds. So there's my conversion, right? So in other words, if I want to know what time is, I'm going to take this equation, or a proportion of theta over 360 is equal to t seconds, the partial or proportion or part of a whole day, which is actually a whole revolution of the Earth, is 86,400 seconds. And I'm going to solve for t seconds. So I'm going to cross multiply, right? So I'm going to get, this becomes t seconds is equal to, I think I just multiply both sides by 86,400, right? So I say 86,400 seconds times theta all over 360 degrees, or 8.64 times 10 to the, what is that? 1, 2, 3, 4, right? 10 to the 4. And then our theta was 3.66 times 10 to the negative 2 degrees, and this was seconds, all over 360 degrees. So the degrees cancels with the degrees, right? I have the little degree symbol here. That cancels with this little symbol here. If I just look at the order of magnitude, I've got 10 to the 4th times 10 to the negative 2. So I should have somewhere along the lines of like 10 to the 2. So if I do all the math on this, I should get 8.8 seconds. So I'm going to do this on my little calculator real quick. I'm going to say 86,400 times 0.0366 divided by 360. Yep, I get 8.78, and we'll just round it to, why is this acting goofy today? .8 seconds. Are Are there any questions?
Am I in the right class?
I don't know. Give me 1 second here. Let me see.